Welcome back to the Science Corner. For all you intellectually curious folks out there, today we're going to take a deep dive into something pretty fascinating, electrowinning. More specifically, we're looking at how it's used to extract and refine metals using electrolysis.
A very intriguing area
But
indeed.
yeah, and it's particularly relevant now with all the talk about resource recovery and just making industrial processes more efficient. We had some really interesting articles from you guys, and we're eager to dig into them and see what we can learn.
Absolutely.
So we've got this piece here from the JOM Journal of the Minerals, Metals, and Materials Society. It seems to be making a case for the future of copper electrowinning, which is pretty interesting.
Yes, a lot of potential there.
Then we've got this in-depth look at improving the efficiency of copper electrowinning. This one's from the Journal of the Southern African Institute of Mining and Metallurgy. It looks pretty detailed.
Oh, it is. It gets into the nitty-gritty.
And for a more basic understanding, we've got this comparison of electrolysis and electrowinning. It's from Process Machina Gold Refining. It seems like a good place to start.
I agree. It lays a good foundation.
Right. And to kind of broaden things out, we'll touch on some related electrochemical stuff from a paper titled Electrolyte Spraying Within H2 Bubbles During Water Electrolysis. And we also have some cool examples of how electrowinning is being used from science.gov. Should give us a good overview.
Sounds like a comprehensive set of resources.
Yeah, definitely. So as we go through all this, what we really want to get is a solid grasp of, well, the basic principles of electrowinning, how it actually works.
Right.
We also want to see how it's used, especially in recovering and refining metals to a high purity. And then, of course, we want to understand what factors affect its efficiency.
Crucial aspects.
Definitely. But, we want to keep things clear and understandable. We don't want to get too bogged down in the technical details. So first things first, maybe we should just define electrowinning. Like, what exactly is it?
Well, based on the information from Process Machina, electrowinning at its core is a process used to obtain high-purity metals from solutions that are rich in those metals.
Okay, so we're talking about solutions like liquids.
Exactly. And these solutions are typically created through a process called leaching. Essentially, the target metal is dissolved from a raw material, like an ore.
So we're kind of pulling out the metal we want from, like a mixture.
Precisely. Then, during electrowinning, you pass an electric current through this metal-rich solution.
Okay, so that's where the electro part comes in.
Exactly. This electric current drives a chemical reaction that causes the metal ions in the solution, which have a positive charge, to move towards a negatively charged electrode. This electrode is called the cathode.
Got it. So we're using electricity to move the metal around.
In a way, yes. As these metal ions reach the cathode, they gain electrons. This process is known as reduction. And as a result, they deposit onto the cathode's surface as pure metal.
So it's like we're pulling the metal out of the solution and pleating it onto this cathode thing.
That's a good analogy.
Now, Process Machina also makes this distinction between electrowinning and electrolysis. What's the difference?
Well, both electrowinning and electrolysis use electrical currents to drive chemical reactions that wouldn't happen spontaneously.
Okay.
However, electrolysis is a broader term. It refers to any process where electricity is used to break down a compound or make a chemical change happen. Electrowinning, on the other hand, is more specific. It's focused solely on extracting metals from a solution that contains their ions.
So electrowinning is like a subset of electrolysis.
That's a good way to put it.
And is there a difference in how they're actually set up, like the equipment and stuff?
Yes, there are some key differences, especially when it comes to the electrodes. In electrowinning, the anode, which is the positively charged electrode, is usually inert.
Inert. So it doesn't really react or anything.
Exactly. Its job is basically to conduct electricity and help facilitate the counter-reaction, which, in solutions with water, often involves oxidizing the water to produce oxygen gas and hydrogen ions. The metal ions, as we discussed, are reduced and deposited as pure metal at the cathode. But in some electrolytic processes, particularly those used in metal refining, you might actually use an impure sample of the metal as the anode.
Huh, interesting.
As the current flows, this impure metal anode dissolves into the electrolyte, and then the pure metal is selectively deposited at the cathode. This leaves the impurities behind in the solution or as a sludge at the bottom.
So with electrowinning, we're starting with metal ions that are already in a solution. But with some types of electrolysis, we're actually creating those ions from a solid anode.
Precisely. That's a key distinction.
Okay, that makes sense. Now, can you use either technique for any metal, or are there limitations?
Well, electrolysis, being broader, can be applied to a wide range of elements and compounds. It's used to produce aluminum from its oxide, chlorine and sodium hydroxide from brine, even refining precious metals like gold and silver.
Wow, so it's pretty versatile.
It is. Electrowinning, though it can be used for gold and silver too, is more commonly associated with base metals like copper, nickel, and zinc. These are typically recovered from leach solutions derived from ores. As Process Machina highlights, it's a cornerstone of hydrometallurgy, which is all about extracting metals from aqueous solutions.
Interesting. Now, everyone's talking about energy efficiency these days. How do the two processes compare in that regard?
Generally, Process Machina suggests that electrowinning can be more energy efficient per kilogram of metal recovered compared to some electrolytic processes, especially those that involve breaking down very stable compounds.
Makes sense.
The reason for this is that the metal is already in ionic form in the solution, so you need less energy to get it ready for deposition. But of course, the actual energy consumption depends on many things: the metal concentration, the conductivity of the electrolyte, the current density used, etc.
So electrowinning seems like a more focused and often more energy-conscious way to extract pure metals from a solution.
I would agree with that assessment.
Now, to see how widely electrowinning is used, we can look at some examples from science.gov. It's pretty amazing.
Yes, the applications are quite diverse.
So, for example, it's used a lot in producing high-purity copper cathodes from copper oxide ores.
Right, that's a major application.
It's also being explored for recovering gold from thiosulfate leach solutions, particularly from recycled printed circuit boards, which is great for sustainability.
Absolutely, it's a key technology for the circular economy.
And in the nuclear industry, they're looking at using it to extract uranium and plutonium from molten salts. This could help with reprocessing spent nuclear fuel, which is pretty important.
A very specialized but crucial application.
And then there's the recovery of other valuable metals like lead and cobalt from industrial waste streams. So it's not just about copper, is it?
Not at all. It has a significant role in responsible resource management.
Okay, so let's zoom in on copper electrowinning for a bit. The JOM article and the Southern African Institute study give us a deeper look at that. What are some of the key takeaways there?
Well, the JOM article really focuses on the future of copper electrowinning. It emphasizes that it's still incredibly important and has a lot of room for innovation.
Makes sense. Copper is still a vital metal.
Absolutely. And the study from the Southern African Institute highlights a major challenge: the substantial electrical energy consumption of copper electrowinning. In plants that use heat bleaching, followed by electrowinning, they found that electrowinning can consume a huge chunk of the total energy, sometimes as much as 60 to 80%.
Wow, that's a lot. So improving efficiency is really important.
It's crucial, both for economic reasons and to reduce the environmental impact of copper production.
Now, the study mentioned something called current efficiency. What exactly is that and why is it so important?
Current efficiency essentially tells us how well the electrical current we're putting into the electrowinning cell is being used to deposit the copper we want at the cathode.
Okay.
It's basically a ratio: the amount of copper deposited compared to the maximum amount that could be deposited based on how much electricity we're using, as per Faraday's laws of electrolysis.
So ideally, we want that ratio to be as close to 100% as possible.
Exactly. That would mean all the electrical energy is going towards pleating the copper. Even small deviations from 100% can have big economic and environmental consequences, especially when you consider the scale of copper production.
Right, because if the current efficiency isn't perfect, some of that energy is being wasted.
Right, precisely. And that wasted energy usually goes towards driving other unwanted electrochemical reactions.
Like what?
The most common one is the electrolysis of water itself. This produces hydrogen gas at the cathode and oxygen gas at the anode. It uses up electricity, but doesn't produce any copper.
Makes sense.
Plus, if there are impurities in the electrolyte, like iron or manganese ions, they can also react to the electrodes, further reducing the current available for copper plating.
So impurities can also mess things up.
They can, yes.
Now, the Southern African Institute research pinpointed something they called metallurgical short circuits or hot spots as a major problem.
Yeah.
What exactly are those?
Basically, they're unintended paths for the electrical current to flow within the electrowinning cell.
So the current is taking a shortcut instead of doing what it's supposed to.
Exactly, and this can happen for various reasons. Sometimes conductive copper nodules grow on the cathode and touch the anode, creating a short circuit. Other times, the electrodes themselves might be warped or misaligned, bringing them too close together.
Okay.
And when these short circuits occur, a large part of the current flows directly between the electrodes without actually plating any copper. This just generates heat, which is a waste of energy.
Got it. So how did they even find these hotspots?
They used infrared cameras. These hotspots get hotter than the rest of the cell because of the wasted energy being converted to heat. So they show up as bright spots in the thermal images.
Clever.
It's a very effective way to pinpoint problem areas.
And then they used something called statistical process control, or SPC, to deal with these hotspots, right?
Yes, they did.
Can you explain how that works?
Sure. Statistical process control, or SPC, is a data-driven method for monitoring and controlling a process to ensure consistent quality and improve efficiency.
Okay.
In this case, they used SPC to systematically identify, analyze, and reduce the occurrence of these energy-wasting hotspots.
I see.
They used a few specific tools. Process control charts track the frequency and severity of hotspots over time so the operators could see when things were going wrong. Pareto charts help them prioritize different potential causes based on their impact so they could focus on fixing the biggest problems first. And Ishikawa diagrams, sometimes called fishbone diagrams, allowed them to brainstorm and categorize the various root causes of these short circuits in a structured way.
So they were really digging deep to understand the problem.
They were. It was a very systematic and data-driven approach.
And once they figured out what was causing these hotspots, what did they do about
And
it?
he created an out-of-control action plan, or OCP.
Sure.
It's a set of procedures they would follow whenever the process control charts show that the process was going off track, like when there were too many hotspots.
Okay.
The OCIP included a bunch of practical measures to eliminate or reduce the root causes they identified.
Like what?
Well, they started by closely monitoring existing hotspots and fixing them immediately. They removed any copper nodules on the cathodes that could be causing short circuits. They also double-checked their calculations for current efficiency and made sure they were accurate.
Sounds thorough.
Oh, and they also focused on controlling impurities in the electrolyte, like manganese and iron, which can affect the copper deposit and lead to those nodules forming.
Got it.
They even improved their routine maintenance. They cleaned the anodes and the cells more frequently, made sure the electrodes were properly aligned and spaced, straightened any bent electrodes, and replaced any damaged ones or missing insulators.
So they basically tightened up the whole process.
They did, yes. They even paid attention to the electrical contacts to the anodes to make sure everything was conducting properly.
So did all of this actually improve their current efficiency?
Yes, significantly. The study found that by implementing this OCIP and getting those hotspots under control, they improved their average current efficiency by 5.40%.
5.40%, huh? That doesn't sound like much.
It might not seem like a huge number, but when you consider the scale of their operation, it translated to a significant increase in production. They were able to produce an extra 74 tons of high-purity copper in just 1.5 months.
Wow, okay, that's impressive. So a small improvement in efficiency can make a big difference in output.
Absolutely, it highlights the importance of optimizing these processes.
Now, besides those hotspots, did they find anything else that affected current efficiency?
They did look at other factors, like the rectifier current, which determines the overall electrical current going to the cells, the current density, which is the current per unit area of the electrode, and the electrolyte temperature.
And did those things matter?
They did find some correlation between those factors and current efficiency, but it wasn't as strong as the correlation with the hotspots.
So dealing with those hotspots was the most important thing for them to improve their efficiency.
It seems that way, yes.
Now, we've talked a lot about copper, but electrowinning can be used for so much more. The examples from science.gov really show that. Can you tell us about some of those other applications?
Of course. One interesting example is the recovery of gold from electronic waste, like those printed circuit boards we mentioned earlier. They use a solution that specifically dissolves the gold, and then electrowinning is used to deposit the pure gold onto a cathode. What's neat is that this method allows them to recover the gold before other metals like copper, which could make the recycling process more efficient.
That's really interesting.
And in the nuclear industry, as we mentioned, electrowinning is being considered for recovering uranium and plutonium from molten salt mixtures. This is important for reprocessing spent nuclear fuel and could lead to better separation of those elements from other byproducts.
So it has applications even in high-tech areas like that.
Exactly. Then there's the recovery of lead from the byproducts of lead-acid battery recycling. They leach the lead compounds out and then use electrowinning to recover the pure lead.
Okay.
It's a much cleaner alternative to traditional smelting, which is pretty energy intensive. And there's also research into new materials for the anodes. For example, they're looking at alloys that can reduce the energy needed for the process by lowering the overpotential for oxygen evolution.
So it sounds like electrowinning is not just about producing metals, but also about recovering them from what we might consider waste.
That's right. It's becoming increasingly important for a circular economy where we reuse and recycle materials as much as possible.
What other interesting areas are being explored with electrowinning?
Well, there's research into closed-loop processes that use citrate solutions to extract metals like copper, lead, and iron from electronic waste. The nice thing about these systems is that the citrate solution can be regenerated and reused, which minimizes waste. They're even adapting electrowinning to produce highly reactive metals like calcium, though that often requires more specialized setups. And researchers are exploring new composite anodes that combine the corrosion resistance of titanium with the electrochemical properties of lead.
Wow, so they're really pushing the boundaries of what's possible with electrowinning.
Absolutely. And with the rise of electric vehicles and all sorts of battery-powered devices, there's a lot of interest in using electrowinning to recycle those batteries.
Yeah, that makes sense. Batteries contain a lot of valuable metals.
They do. Yeah. And electrowinning is proving to be a very effective way to recover those metals.
Mm.
For example, one approach uses supercritical carbon dioxide to extract specific metals from battery waste, and then they use electrowinning to get high-purity cobalt.
So they're using electrowinning to essentially mine those old batteries for their valuable components.
Exactly. It's a much more sustainable way to get those metals than traditional mining. And there's also work on using electrowinning with a ferric-ferrous redox system to recover copper from printed circuit boards. This system is interesting because it allows for both copper deposition and the regeneration of the ferric oxidant, making the process more efficient. And they're even recovering tin from those boards using alkaline leaching, followed by electrowinning. And then there's this innovative electrogenerative process for recovering gold from cyanide solutions.
Cyanide. That sounds dangerous.
Well, cyanide is sometimes used in gold leaching, but this new method can recover the gold very effectively and hopefully more safely. They've been testing various cathode materials, and porous graphite and reticulated vitreous carbon seem to be the most promising.
So electrowinning isn't just for large-scale metal production anymore. It's also a key technology for recycling and sustainability.
It is, and it's becoming more important all the time. The demand for those metals is only going to increase as we move towards a more electrified future.
Now, we also looked at this paper on water electrolysis. While it wasn't about metal electrowinning specifically, did it offer any insights that could be relevant to our discussion?
It did, actually. The paper focused on the fluid dynamics of gas bubble formation during water electrolysis. It showed some really interesting things happening at the electrode surface where the reaction takes place.
Okay.
For example, they observed the formation of tiny gas bubbles that grew and combined into larger bubbles. They even saw tiny droplets of the electrolyte being ejected within these gas bubbles as they detached from the electrode.
Interesting.
And they talked about something called Marangoni convection, which is a type of fluid flow driven by differences in surface tension. This can happen when there are variations in temperature or the concentration of dissolved substances at the surface of a liquid.
So basically, if one part of the liquid surface is hotter or has more stuff dissolved in it, it will flow towards a colder or less concentrated area.
Exactly. And this convection can affect how ions move within the electrolyte, which is important for electrowinning because those ions need to reach the electrodes for the reaction to happen.
Makes sense.
Now, how does this relate to metal electrowinning? Well, those gas bubbles forming at the electrode can actually be a problem.
Oh, how so?
They can act as a barrier, making it harder for the metal ions to reach the electrode surface where they're supposed to be deposited. This can reduce the efficiency of the process.
So those little bubbles can have a big impact.
They can.
Yeah.
And the paper also discussed aerosol formation, which is relevant to the problem of acid mist in some industrial electrowinning processes.
Acid mist.
Yeah, in some cases, the electrolyte can form a mist that gets released into the air, which is obviously not good.
Definitely not. So understanding these things can help us make the process safer and more environmentally friendly.
Exactly. It highlights the importance of understanding what's happening at that electrode-electrolyte interface.
So even though the paper was about water electrolysis, it still sheds light on some important aspects of electrowinning.
It does. It shows how seemingly unrelated research can provide valuable insights that can be applied to other areas.
Well, this has been a really fascinating deep dive into electrowinning. We've learned about its basic principles, its importance in producing and refining metals, and its growing role in resource recovery and sustainability. It's amazing how this relatively simple electrochemical process can be applied to so many different areas.
I agree. It's a testament to the power and versatility of electrochemistry.
And the research we discussed, like the work on statistical process control, shows how we can constantly improve these processes to make them more efficient and environmentally friendly.
And the ongoing research into new materials and techniques is really exciting. It suggests that electrowinning will continue to play a vital role in the future of metal production and recycling.
It's clear that electrowinning is much more than just a way to make metals. It's a key technology for building a more sustainable future. So, to our listeners, what questions do you have about electrowinning? Are there any specific metals or recycling processes that you'd like to learn more about? We'd love to hear your thoughts and maybe even explore them in a future deep dive. Thanks for joining us on the Science Corner.
It's been a pleasure.
Until next time.